Okay, I want to talk a little bit about metadata. What is metadata? Metadata is information about a data set. It's prepared to help users understand and apply data properly. Contains information on structure and meaning. It cites sources and credits for the data. It describes access and use constraints, and it can be part of a data set or in addition to it. So it's some cases stored with the data, and some cases you have to download it separately. But to wrap it up in a nutshell, it's simply data about your data. Um, Metadata a lot of times looks like this. It contains information about the data that people need in order to evaluate its quality. Metadata is the primary means by which you make that determination of data quality. And remember that the definition of data quality, quality data is data that is suitable for an intended use or purpose. So metadata is the means by which you make that assertion. If data is available and distributed publicly, metadata should be provided with it. There is a Federal Geographic Data Committee, the FGDC. They define and manage the standards for metadata, and they also define the standard content and format so that metadata can be shared across platforms. This was important because prior to having any sort of a committee that set these standards, there was not really much in the way of guidance, and metadata could vary significantly, and still does, but it was even worse before. So why do you have a standard? Makes it so much easier to share metadata. It comes up and provides a single format so that all the software manufacturers have a guideline to go by, and it also defines what type of information everyone expects to be included. We here in the U.S. use the U.S. federal standards, which is the content standards for digital geospatial metadata. There's also various international standards as well. The primary purpose is to document the original source of the geospatial data sets, to document the circumstances under which the data are assembled and processed, and to provide a lasting documentation about the data, explaining things. And this allows people to look at the data set and then to make truly educated decisions about whether it is of sufficient quality for an intended use. So let's talk a little bit about data quality. Data sets are rarely perfect, and there is no such thing as an absolute standard for data quality. It just doesn't exist. Quality is defined as the fitness of a data set for a particular purpose. Some data sets work for one thing but not for another. You, as the geospatial professional, you have the ethical and legal responsibility to determine if a data set is sufficient for its intended use. Now, one of the things that comes up a lot is students will say, but this data just isn't good enough. What do I do? Well, if it's the only data that's available, then you're going to use it. But you have to, in the process of generating that report or that document or that map, you need to make it clear that there were limitations and constraints in terms of your data quality, and that you did the best you could with what you had, and that if you had better data, you may end up with a different determination. When we look at data quality issues, there's really just 6 of them. Lineage, positional accuracy, attribute accuracy, logical consistency, completeness, and temporal accuracy. Lineage is simply that detailed listing of how you got from when the data was originally collected to the piece of information that you're looking at, what was done to it by who and how. Positional accuracy is all about how accurately things are placed geographically. Attribute accuracy is all about the accuracy contained within the attributes associated with the data. Logical consistency speaks to the data interacting with one another in a consistent manner with the way it exists in the real world. In other words, underpasses and overpasses is always the best example. Is it an intersection, an underpass, or an overpass? Logical consistency dictates that these things in the GIS should behave the same way that they do in the real world. And so just because the lines cross doesn't mean it's an intersection. It's an intersection if it's an intersection. It's an overpass if it's an overpass. It's an underpass if it's an underpass. Completeness speaks to any missing data, whether it's attributes or otherwise. And then temporal accuracy is all about when the data was collected, how long and how reasonably long you can expect to use it, when is it updated, that kind of stuff. Anything in which time could impact the quality. Again, where did it come from? What did they do to it? That kind of stuff. Source scale is also something that plays into a lot of this. Data that's developed at one scale is not necessarily useful at another. When you look at features at certain scales, shapes change. Cities become points. Curvy roads become straight lines. So you have to take into consideration the scale at which the data was developed. Here's a really good example of why. Two lines, same place, both are correct. One's at 1 to 5 million scale, one's to 1 to 25 million scale. At a certain scale, things will start to look differently. If you're not sure what the source scale is, it should usually be in the documented section of the metadata. Lineage, again, all the processing steps, who did it, when they did it, any kind of transformational errors, that sort of stuff, what software was used, all that. Here's an example of what a really good lineage document would look like. Positional accuracy, how close to features in the data set correspond to their actual positions in the real world. You say a line's here, a road's here, how accurate is that? How is the road where it's supposed to be? That is positional accuracy. Geometric accuracy, this is more than is it where it says it is. This is the level of error in the original source, plus all the stuff that goes into it, plus are we identifying things correctly. And this can manifest in a lot of different ways. Driveways being mistaken for roads, shadows being mistaken for houses, roads not lining up, lots of different ways. Precision is simply the number of significant digits in a measurement, and statistical variability of a repeated measurement. It's not the same thing as accuracy. Scale and precision. This is something we need to talk about a little bit because it matters, but it's not something we have to spend hours on. So we're going to use this equation here where it says S. Let S be the size of the highway, and it's represented by a 3-point line symbol. All right, so you have this highway, and you got this line here. It's 3 points. 1 inch is equal to 72 points. So if we're at 3 points, and the map is at 1 to 100,000 scale, then if you solve for S, you end up with a situation where S equals 3 million point or 300,000 points, which loosely translates into 4,166 inches or 347 feet. So why does this matter? That 3-point line that you're using there to represent that road, is that road 350 feet wide? Probably not. So there's going to be some uncertainty, especially when you start doing things like intersects and that kind of stuff. And particularly when you look at the map, not so much when you do the intersects, but when you look at it, that's when it really begins to show. So automatically, we have this wide range where we're saying is sort of the line, and what it does or does not come in contact with when you look at the map visually is greatly impacted by the choices you make, like how thick you make that line. Now, you can only mate it down to a 1 point thickness, or well, you can mate, I guess, a half. But if you went to just one, at a minimum, you're still looking at it like 110 feet across. So you start to sacrifice accuracy on what you can visually see on the map if you try to keep things in the more perspective sizes. I guess what I'm trying to tell you is it's important to recognize that the thickness of lines, which seems like just simply something to look at, has a practical implication on the quality of the map. National map accuracy standards were something that were developed, and basically folks are supposed to follow these. Are stringent quality assurance and control procedures when you produce a base map, and a base map is something that is an underlying background map. The national map standards specify the procedures and quality guidelines for testing the accuracy and all this kind of stuff. It basically consists of 20 checkpoints, well-defined and locatable points that correspond to locations on a reference map that's of a better accuracy. No more than 10% of the points can be off by more than 1 in 10,000 units. And it's a pretty tight accuracy. However, almost no maps are ever actually tested. However, you can assume that the quality base map products from USGS and other quality providers conform to this map accuracy standard. Stuff that some guy on ArcGIS Online named Todd made, not necessarily the case. A wonderful base map of whatever that Jenny261 made, you have no idea. Practical rule of thumb assumes that a typical line width on a map is a 0.5 millimeter, and a map scale. So if you take the map scale and divide by 2,000, it gives you the approximate precision in meters. So if you take 5,000 and you divide it by 2,000, you get 2.5. So about 2.5 meters is the accuracy of a typical line on a 1 to 5,000 scale map. Just keep that in mind. Processing effects do more than just create cool products. They can degrade the spatial accuracy of data. There are associated errors and tolerances that you need to report in the process steps and consider in your positional accuracy reports if you're filling out a full metadata. Georeferencing or registration errors are usually recorded as the root mean square error. The geoprocessing steps, like intersect and buffer, they're executed with larger XY tolerances to control slivers. Any of these things you do can impact the final product quality. Attribute accuracy assesses how well attribute values correspond to the values in the real world. This is exceedingly complex, and basically what Price says is there's as many ways to assess this as there are attributes to assess. We're talking about everything here from correct data entry of addresses to the right number of decimals to using scientific notation and significant figures when you're recording stuff. There's all kinds of things that could conceivably contribute to attribute accuracy. Thematic accuracy is a little different. It's like looking at a map and assuming the map has a theme, okay? And then thematic accuracy is simply how accurate that theme is based on the stuff that went into making that theme. So if you have a map at tree crown density, what matters is how accurately it is portraying the tree crown density. In order to make that assessment, you need to know things like how is it measured, how accurate were the measurements, what are the potential sources of error, that kind of stuff. Again, these are not easy things to assess. Measurement errors. What's the precision and accuracy of the instruments? Did you use a GPS unit where you're in the forest? Could there have been signal dilution from the tree cover? Was things bouncing off of stuff where you're in a canyon? How measurable was the phenomena? Is the geologic contact visible, or are you assuming it's there because of some change in the landscape you're seeing? Um, can the census legitimately count every person? How accurate can they do that? That's a good question. How homogeneous is the measurement over the measured area? So if you're measuring some value and you're measuring it across an area, is that measurement consistent or does it change wildly? And if in which case, did you take enough measurements? Are you aggregating those measurements or are you keeping them individual? Now, all these things go into it. Classification issues. How fine was the original measurement scale? We'll talk about the precision that can affect your classification. How are you classifying the data? Why are you classifying it that way? Do the class breaks you choose, are they based upon the distribution? Some, a little. Did you use Jinx natural breaks? Why? Why not quantiles? These are the things that could make your outcomes different. Just basic errors, mistakes. How often are they made? Um, did anybody bother to check to see if you could find any of them? And how often are things that you have recorded simply wrong? Not, decimal in the wrong spot, wrong plus or minus sign, but simply not correct information. When we assess attribute accuracy, it requires detailed and advanced knowledge of a lot of things. How was it collected? What were the instruments? What was the post-processing? What's typically expected? Again, super challenging. And basically, you kind of got to just assume that everything is going to be okay. And what we do with a situation like this, it says it's okay to not know if you really don't know. What that means is stuff like this is going to be terribly hard to ascertain. And so some of it's going to come from the reputation of the data source. So some guy on the internet named Todd, you have no way of knowing, anything about that. Jenny867 on ArcGIS Online. Well, what does that mean? Who knows? Comes from the USGS Office of whatever. Now that's got some more gravitas to it. That's something that we can associate with as being of a potential quality. Rule of thumb. If you're getting something like, for example, census data, where would be a good place to get that from? U.S. Census Bureau? Yeah. Perhaps some sort of state or county agency? Maybe. At the state level, I would be more comfortable with it, but at the county level, it's only as qualified as your local county GIS professionals. And in some counties, that is completely unqualified. Some cities, completely unqualified. So as you become a smaller entity, your assumed technical expertise becomes more questioned, and the quality of the products that you're providing without documentation would become much, much more suspect. We talked a little bit about logical consistency. Again, it describes how well features mimic real-world situations, and some ones we typically come across that we can test for are basically topological errors, coinciding boundaries where there's gaps and overlaps, where lines are supposed to meet and you end up with undershots and overshots. improper intersection. So should it be an intersection, underpass, or an overpass, and it's just wrong. Pseudo-nodes and lines and loops. These are all just types of errors that there is language that allows you to test for these things. Completeness. Did it capture everything that it was supposed to capture? Again, really hard to quantify. Polygons is the entire area covered. How small an area could you have mapped? Lines and points. Did the DOT map every single record? Are intermittent and perennial streams included? A lot of this just comes down to reading metadata just to understand when they give you a line for a stream, what that actually means. What did they consider a stream? What did they not consider streams? When they have points for springs, is it perennial? Is it wet season springs? You know, that is why metadata is important, because you may think you've got every stream and you've only got, second order high volume type streams or something. Temporal accuracy. How well the information at the time of production still represents the current ground conditions. This is probably the most profound statement that you'll see in terms of any of these individual accuracies. So it's not so much is the data new as it is has time impacted the data. In other words, if over time that data is expected to change, then the time that's passed since the data was collected is important. If the data is not expected to change over time, then it doesn't matter if it's 5, 10, or 15 years old or older. Certain data changes at different scales. Certain things are virtually invariant. Geological maps, digital elevation models, basically they don't change. Other things change over a longer period of time in terms of decades. Things like land use, vegetation maps, earthquake maps, that sort of stuff. Other things change much more frequently, like at a yearly scale. Census data, drought, crop production. Other things are what we call ephemeral. In other words, they change all the time. Best examples of that are like radar maps of storms. They change literally minute by minute. Your metadata itself is divided into 7 sections. These sections vary a little bit from standard to standard, but we're going to go with the basic FGDC standard sections: identification, data quality, spatial, data organization, spatial reference, entities and attributes, distribution, and then your metadata reference. So here's what those things are. Identification is just basic information like title, area, any keywords, rules for acquiring and using the data, that sort of stuff. Data quality is the general assessment of the position and attribute accuracy, the completeness, and consistency. Data organization talks about how the data is organized and formatted, whether it's vector, raster, that kind of stuff. Spatial reference is all the properties of the spatial coordinate system, including the projections, datums, and various things like XY extent. Entity and attribute information are also important. This is information about the content, things like names and definitions, so that you understand what abbreviations or field names are and what they mean. Distribution information, how to get the data, what you can do with it, that sort of stuff. And then last, your metadata reference is information on who created the metadata and how they organized it. In order to be FGDC compliant, you have to have these fields. They all have to be filled out. If they're all filled out, it's compliant. If you plan to distribute data to others, then you should at least have FGDC compliant metadata. Data contracts usually include this as a condition for contract completion. So if you're going to do contract GIS work somewhere, a lot of times the first thing that's going to happen is they're going to require it to have competent, complete, compliant metadata.